Hi grade 12s, great to be with you. Now today we're doing organic chemistry. We're starting off by looking at organic molecules in this session. There are a whole lot of things that you need to know, and you need to remember that organic chemistry carries quite a number of marks, a large percentage of marks for paper 2. Let's get into what you need to know about organic molecules. Here's your checklist. I want you to make sure as you prepare for the exams that you can name and draw structural formula of organic molecules by following the IUPAC rules. Now we're going to do quite a number of examples, but we won't be able to do all of them. You need to really make sure that you understand the nomenclature. That's a fancy word for saying the naming of organic molecules, and be able to draw the structural formulae. Structural formulae, remember, are those that show all the bonds. And we must, when we're drawing structural formula, indicate all the bonds, not just draw sticks onto C's. We must fill them all in. Make sure you get that right. The next one is that you must be able to identify the effects that size, shape, and functional groups have on the physical properties of organic molecules. This is extremely important, and there is bound to be a question where you're asked to relate the structure of the molecule, the intermolecular forces, the energy that's required to break those intermolecular forces or weaken the intermolecular forces, and how that relates to the physical properties. Now, in terms of the physical properties you need to know, you need to be able to explain boiling point, melting point, and you also need to be able to explain saturated vapor pressure or vapor pressure. Those are the trends that we're going to be looking at, and it's very important that you be able to explain it in a logical sequence. We'll be going through an example of that so that you get it correct. The last point that I want to make for today's session is that you should also remember that polymers are organic molecules. And apart from the fact that we can name organic molecules, it's likely, I think, that in the final exam you will be asked something about different polymers. But there are a limited number of questions according to the exam guidelines that you can be asked. So make sure that you revise that section. I'm not expecting a huge number of marks to be allocated to polymers, but you do need to know the basics of polymers, and we will go through that. So when we deal with polymers, you should be able to identify, name, and recall the chemical reactions used to make polymers. You really do need to focus on some important facts. Don't get delayed and waylaid about polymers. Obviously, when we talk about polymers, we can also talk about their physical properties, the intermolecular forces, and that could very well come up in the final exam. I don't know what's in the final exam, but reading in the guidelines, it's quite possible that something on polymers will come up. So we'll dedicate a whole question to polymers, and hopefully that will give you a chance to revise. Let's get straight into it, and we're going to start by looking at a question from the November 2013 examination, and you will see and notice that it has been adapted to include the important new topic of polymers. But make sure that you don't forget all the other things. Now, if you go back to previous exam papers, you will notice the organic chemistry questions are all applicable to the CAPS document, except for the ones in 2008 and 2009, I think, where they had something called amines. Amines are not included in your CAPS examination, and neither will be ethers. So don't worry about questions that deal with amines or ethers, but you do need to know the basic hydrocarbons, the alkanes, the alkenes. Remember what a functional group is. Remember what an isomer is. Remember what a homologous series is. And all of those terminologies need to be learned. Now we'll be recapping them as we go through them through this particular question. So let's get straight into it and let's see exactly what it says. They typically, in this sort of question, give you a diagram with structural formulae, and they give you some names And they tell you that letters A to F in the table below represent 6 organic compounds. Now remember the basis of organic chemistry. Organic molecules are those that contain carbon. Carbon always has 4 bonds, and it will link to other substances. It has this amazing ability to form chains or to form rings. You need to know both of those. You need to be able to draw structural formulae like these and to analyze them. So here we've got 6 organic molecules. We recognize molecule A has got carbon and hydrogen in it. Molecule B has carbon, hydrogen, and oxygen in it. Slightly different. Now, as you look at an exam question like this, it's important that you start putting pieces together and you start identifying some things as we go through them. Start to make a few notes, and it might even be useful to do this on your question paper so that you can answer the later questions. Then we've got C is polyethene, and D is pentyl propanoate, and E is something that's got bromine in it, and carbon and hydrogen, and number F has just got carbon and hydrogen. But they're all different. Please notice that even though they have the similar sort of atoms involved in these molecules, they are different. They have different features. We need to be able to look and identify what those features are and therefore be able to name them. Now, the first question that we're asked to do is to write down a letter that represents the following. Let's read the whole question. First of all, we're looking for an alkene, a ketone, and the last one, or the next one says, a compound with a general formula. We'll revise what that general formula means, and a polymer. Now, given those things, we need to be able to identify that special feature of every molecule that we've been given, and so relate to it. So that special feature we call the functional group. Now, if we look at the thing that we're asked to find, an alkene, the functional group of an alkene, remember, is that it contains a double bond between 2 carbons. And strictly, it should only contain 1 double bond. If it was 2 double bonds, then we'd have it as a diene. Now, the other thing that I need you to recall is that every family, like the alkenes, we call that a homologous series. It has a special functional group and it has a general formula. I'm going to write down the general formula so that we can check it. I'm going to put it over here. The general formula for the alkenes is CnH2n. That's the molecular formula. So there's the structural formula with showing all the bonds, and then the ratio of the carbon to hydrogen, which is written here as the general formula. We'll need to check that we've got it correct when we identify the alkenes. While you're revising and you get a question like this, make sure that you don't just remember what the alkenes are, because they belong to a family of hydrocarbons. We should also recall what the alkanes are. Well, what's the special function of the alkane? The alkanes only have single bonds. And what about the alkynes? Well, they have a triple bond, a single triple bond, and the general formula we will come to in a little while. But as you're doing your revision, you're working through previous exam papers, make sure that you're revising all those factors so that you can identify. So we're looking for an alkene. Doesn't tell us how many carbons are on this alkene, but let's go and eliminate and check that we've got things right. I'm going to work in this orange pen. Now, over here in number A, we've got a single double bond. It immediately lets me know that this is a possibility for an alkene. Right. Let's see, are there any other substances? Well, we recognize the second rule about alkenes is that they only have hydrogens and carbons. So notice that this one only has hydrogens and carbons, and it also has a single double bond. So in my books, this fulfills the criteria for an alkene. But there's one last thing that I want to do, just to make absolutely sure. I'm going to write down the molecular formula, and I'm going to put it on the diagram. I'm going to count the number of carbons. And so let me just get the eraser so that we don't that we can see more clearly. And I'm going to count it according to the IUPAC rule of counting and numbering, so that we can also work out the name of it, even at this stage, that we're not really asked to do that. So these are things and thoughts that are going through my mind. So what I'd recognize is I'm going to start closest to the double bond, and I'm going to therefore say, I'm going to start from the right-hand side, and I'm going to say 1, 2, 3, 4. Now I need to make sure I've got the longest chain. Always identify the backbone or the longest chain. That's number 4 so far. If I go down there, it means 5. It can certainly go longer if I go to this one. So that one I'm going to call 5. That one I could call 6, or I can call that one 6. It doesn't matter. I prefer to work in a straight line. But remember, it's possible that you can get turning the corner and getting longer. If it goes turning the corner and going longer, then you must include that as your longest chain. So at the moment, I've got 6 carbons in the longest chain. So there's my longest chain. Now, what other carbons have I got? Notice I've got a side branch over here, and I've got another side branch. So in total, I've got 8 carbons. So that's the molecular form, the start of the molecular formula, C8. I now need to count the number of hydrogens. Let's do that. Well, I'm going to now erase, just so that we've got it a little more clearly. We've got the number of carbons. We recognize it's 8 carbons. Just erase my working so I can, that you can see a little more clearly. I'm going to start counting the hydrogens. I'm going to say I've got 3 hydrogens there. I have 2 hydrogens here. So that's 3, and over there is 2. I have another 3 over here. That's the methyl group on the side branch. I have 1 over there. So that's 1. I have 3 on this one. Put that in brackets. I have 1 over there, and I have 3 on this end. So let me add up all the ones that I've now indicated and make sure that I get them right. So 3 and 2 is 5, and another 3 is 8, 9, 10. 10 and 3 is 13, and 3 is 16. So if I write this down, I'm going to write it as the formula C8H16. Does it match the general formula for the alkenes? What was the general formula for the alkenes? Remember, we wrote it over here. Cn, and we're saying N is 8. Then what is 2N? 16. Yes, the alkene is A. Now, before we carry on, are there any other alternatives? Let's go and look at the other options. Well, there's a double bond, but it's got oxygen. So that we know is not an alkene. Polyethene, well, look, it does seem to have, and this is a bit of a tricky one, in the name, it ends in ENE. But is it an alkene? Well, it's got poly in the front, and we're going to need to revise what polyethene is. It means that the monomer, the starting point, was ethene. But when it joined together, all of those units, they lost their double bond and they became separate units. So they are totally saturated. Remember, alkenes are unsaturated. We can add to them, get an extra hydrogen in them. So it doesn't give us the maximum number of partners. But ethene, polyethene, is a saturated polymer. So it can't be that one. What about the next one? The next one we've got to is pentyl propanoate. Now, immediately we read that, we recognize it doesn't fit into the naming structure of a alkene. So it can't be that one. We're just making sure that we haven't missed one out. Well, what about this one? Well, first of all, I recognize there are bromines there. Now, as soon as you've got something else added to it, it can't be a hydrocarbon. We've got a halogen added. This means that it is a halo, and we recognize they're all single bonds, so we would say it's a haloalkane or an alkyl halide. Okay, those are the 2 words that we would name for that particular functional group or family that we're looking at, homologous series. So it's certainly not that. Now, what about the last one? Guys, have a careful look here. We've got a triple bond. Triple bond between carbons tells us that this is an alkyne. It's only got hydrogens and carbons in it, so it certainly fits into the category of a hydrocarbon. So it could be an alkane, or alkyne. But this one has a triple bond. If it's got a triple bond, 3 lines being shown there, it must be an alkyne. So yes, we've got the alkene correct, and we can move on to the next question. Next one, ketone. Now, the ketone is an interesting functional group. The ketone has what we call a carbonyl group in it, a double bonded oxygen linked to a carbon. The word that we're looking for there, carbonyl. Now, there are a number of homologous series that have carbonyl groups in them. The ketone is one of them. The other one that is similar and related to the ketone is something called an aldehyde. And lots of learners get mixed up between the ketones and the aldehydes. And what we need to recognize is it's very simple. The ketone will always have the carbonyl group in the middle of the structure. So it's not going to be on the ends, whereas an aldehyde will have the carbonyl group at the end. So we can eliminate anything that's got a carbonyl group at the end. But the ones that have the middle group, those are ketones. But we need to be very careful. There are other homologous series that also have carbonyl groups. And I just want to revise those very quickly. Remember that you can also get something called a carboxylic acid. And that has a carbonyl group, and it has a hydroxyl group. So you've got to not just look at the carbonyl, you've got to look at what's bonded to it. And in ketones, it will be another carbon on either side. It can't be an oxygen. So in this case, we can recognize that carboxylic acids are not the same as ketones. The other one that can be a little confusing or might lead you astray if you were given the choice between a ketone, and here's another thing that's got a carbonyl group in it. I just want to illustrate it for you. Let's have a look at something like this. If we went, is that a ketone? We recognize it's not on the end of the molecule. That molecule could carry on. It's not on the end. It's in the middle. So is it a ketone? No, it's not, because it's linked to an oxygen. And you should remember and take note that if you get this structure where we go COCO, cocoa is my way of remembering, and cocoa, I remember, is linked to somebody who made perfumes. That person's name was Coco Chanel. Chanel perfume, very expensive, very nice perfume. But those molecules are called esters. So Coco Chanel gave perfume to ester. Now, ester is spelled differently, but I hope that all helps you remember and identify the difference between the ketone and the ester group. Let's just erase that. And now, with that information, go and have a look at what we've got. Are there any ketones present? Well, yes, there is. Look at it over here. There's the carbonyl group. We've already got it. And it's linked to carbons on either side. And so we know exactly that we've got the right one. The answer that we're looking for is B. But please note, when you're doing your revision, don't just rush through it. Try and revise and make sure you've got everything else. The other question that we need to ask ourselves is, when we're making ketones, where do they come from? Well, they come from secondary alcohols. And we need to bear that in mind. Secondary alcohols are those that have the hydroxyl group in the middle, not on the end. Primary alcohol will have it on the end. those will form aldehydes, where secondary alcohols will form ketones. So bear that in mind and make sure that you've got that revision covered as well. So the next one, moving on, is a compound with the general formula CnH2n minus 2. Now remember, the alkanes have the formula, the general formula CnH2n plus 2. The alkenes, as we've seen earlier, have the general formula CnH2n, and the alkynes have CnH2n minus 2. Remember that these ones have single carbon-to-carbon bonds. This one has one carbon-to-carbon bond, and these ones have a triple bond. Now, we've already seen that. Triple bond, alkyne, and we need to make sure that we identify the correct one. Giving the answer, not difficult. We've identified it over there. So the answer that we need to write down for the answer to 1.1.3 is going to be number F. Go over these. Make sure that you understand what the general formula is. Let's just do a final check to make sure that we've got this one right. 1, 2, 3, 4, 5, 6. 6 carbons. How many hydrogens? Let's do them. 3 hydrogens over there, 3 hydrogens over there, 3 hydrogens over there, and 1. So 3, 3, that's 9, 1 is 10. So I would write down the molecular formula of this as C6H10. Now let's check, does it fit the general formula? Well, 6 times 2 is 12, minus 2 is 10. Yes, we know that we've got it right. It does fit the general formula. And for this answer, you didn't even have to really work out that it was an alkene. You could do it by counting and making sure that the general formula fits to the one that you're wanting. Okay, the next one, polymer. Well, polymers are always going to have, in most cases, going to have the word poly in front of it. And the only one that we were given, this isn't all, the one that we were given, is polyethene. So you need to look for the word poly, and so it was a really easy question in terms of that. But please remember that there are other polymers that are not necessarily always going to have the word poly, and we're going to discover that and discuss that a little later. Okay, the last question is one of my favorite questions because it deals with the idea of structural isomers. And I want to just revise for you what a structural isomer is. You say, I remember isomer, isotope. No, well, let's just get it clear. There are all these isobar, iso in other subjects as well. Iso means the same as, okay? So there's something common between them. Iso, got that. Isosceles, the word iso, something is the same. Here, we're talking about structural isomers. And in organic chemistry, we say a structural isomer is the following. It's something that has the same, what? Molecular formula, but it has a different structure, different structural formula. Now, guys, there are different ways of doing this question, and one of the things is that you've been given the name of the substance that you're looking for, its isomer. So let's go and see if we can draw it. We're told we're looking for cyclohexene. Now, the reason I'm drawing it is because we could rush in and make a mistake, and I don't want to do that. The first thing that we start is what's the prefix? Now, you must know your prefixes. When we start, 1 carbon is meth, 2 carbons is eth, 3 prop, 4 bute, 5, you've got it, pent, 6 is hex, 7 is hept, and 8 is oct. Make sure you understand those. and that you learn them really well. When we look at this molecule, we're looking at hex. Hex is 6. So immediately I can say I'm looking for C6. I'm going to look for something with 6 carbons. But it says hexene. So it needs to have a double bond. So the first thing I'm going to do when I draw this molecule, structural formula, is I'm going to draw in the double bond. Then the next thing that it tells me is it's cyclo. So that means it forms a ring. When you see cyclo, it forms a ring. If it doesn't have cyclo in front of it, then it's just a straight chain. So we get rings and chains, and in this case, we're going to fill these in. Now, we want 1, 2, 3, 4, 5, 6, coming back to there. Now, can I just leave my structural formula like that? No, can't do that, guys. I've got to make sure that every carbon has 4 bonds. Always, always, always. 4 bonds. So let's count up the bonds, and we've got to show what they're bonded to as well. So there are 2, and there's 1. So it's missing 1, and because it's cyclohexene, that tells us that it is a hydrocarbon. So it's got to be hydrogen that's bonded in. What about this one? 2 on that, 1 on that. There's the third one, and there we've got the extra hydrogen. So now what about this one? Look, 1, 2, 1, 2. We're needing 2 hydrogens here. And in the same way over here, we're going to need 2 hydrogens. And over here, we're going to need 2 hydrogens. And over here, we're going to need 2 hydrogens. Okay? So what's our next task? We've drawn the structure. We know that it's 6 carbons. We want to be able to work out the number of hydrogens. Well, so let's just count them. So we're going to start off. We've got carbon number 1. That's hydrogen number 1, hydrogen number 2. Now we've got 4 hydrogens. And another 2 is 6. Another 2 is 8. And another 2 is 10. So we're looking for something with a molecular formula of C6H10. Didn't we just come across one like that? And if we are thinking about it as well, we should say, well, this is a hydrocarbon. What's the general formula that fits this pattern? Well, look, it says CnH. If I double that and minus 2, then I'm going to get it. So I'm looking for something that's an alkyne. And we know what the alkyne was. We did it over here. We did it in question 1.3. And we know that F over here has just that formula. It is the alkyne. That's really interesting. We see that we've got structural isomers that don't belong to the same homologous series. Let's just recap on that and make sure that you've got that very clear. So what we recognized that we have here is, let's write it down, cyclohexene has a structural isomer that was an alkyne. In the same way, you need to realize that if we have cyclohexane, it will have isomers that belong to the alkene group. And there's a last one that examiners really enjoy passing over and making questions on that you need to be aware of. Don't just look in the same homologous series for isomers. You have to realize that something like an ester has structural isomers that are carboxylic acids. So make sure you practice naming your different structural isomers and identifying them. They're really important. Now guys, I think it's time for a short break. After the break, we'll carry on with some more questions. Welcome back from the break. Guys, let's get straight into it. The next question asks us to revise the IUPAC naming system. And I want to give some attention to this, and I need you to pay very careful attention. We're asked to write down the IUPAC name for each of these compounds. I've taken them out of the table and redrawn the structure for you, pasted them below, so that we can get the rules right and we can get the complete name. Now, we started on this particular one in the previous question, and we said we always look for the longest chain. First step, look for the functional group. We recognize there's the functional group. Next step, look for the longest chain. So immediately I know there's one double bond, it's a hydrocarbon, and it's going to end in -ene. I'm not even going to write that in the name yet, but it's just a bit of information that I've collected. The next thing is I'm going to look for the longest chain, and I've done it already, so I'm going to say 1, 2, 3, 4, 5, 6. I know that if I went up to the top to this one, to this side branch, it would also have been 6, so I could have chosen that as 6, but I'm not going to. I'm going to keep it in a straight line. Okay? But check your side branches that they don't give you a longer chain. It's possible for something to be branched when you're doing it. So we've got the 6. What does 6 mean? It means hex. So the prefix, not the suffix, it's going to be hex. So these are the bits of pieces that we're putting together. The next thing, having identified my functional group as a double bond, I need to say, where is it? So where is the double bond? The double bond happens to be on carbon number 2, the lowest number. So that's why I wouldn't number my chain from this side. I wouldn't number it. This would be wrong. I don't want to number it 1, 2, 3, 4, 5, 6. The orange writing is wrong. You need to get the position of the double bond as low as possible. So we know that it's at the lowest point. So I'm going to start to write my formula now, or my name. I'm going to say hex as the prefix, position, number 2, and -ene. Now, that's very important. Please recognize 2 things. You must put dashes between numbers and letters and other letters need to be joined together. There mustn't be spaces. The other rule that we need to have is that between numbers and numbers there are commas. Numbers and letters, there are dashes. Numbers and numbers, there are commas. So what else is there added to this lovely molecule? Well, there are 2 side branches. There's one on carbon number 4 and there's one on carbon number 5. What do we call those side branches? Let's identify them. We recognize that that side branch is a CH3. There's 1 carbon and 3 hydrogens. That means it's going to be called methyl. This one is also a methyl. If there were 2 carbons and the extra number of hydrogens, so if we had C2 and in this case you would have H5, then what would you call that? You would call that ethyl. Okay? It's a side branch. Make sure that you've got that correct. If there were 3, it would be called propyl. I'm not going to go over any more of that, but just make sure that you revise that. Okay, so we're dealing with methyls, but we've got 2 of them, guys. So we need to use another nomenclature, another part of the naming process. If you've got more than one of the same thing, if you've got 1, then it's just fine. Then if it was 2, then we say it is going to be di. And if it's 3, then it's tri, and so on. And we generally don't get more than 3, but you can do. And we can put the suffixes in as well. But because we've got 2, we can't just say dimethyl. We've got to indicate the position. So let's do that right away. So I'm going to need to judge my writing because I need to make sure that the methyl lands up correctly. So I'm going to say dimethyl and squeeze it in so that it joins up nicely. If you're playing it and getting it into bits and pieces, make sure that you cross that out if it's not joined together and rewrite it when you've got the final name. Now, where do these fit in? At carbon number 4, we've got 1 methyl group, and at carbon number 5, we've got the second methyl. So we're going to write this full name as 4,5 dash dimethyl hex 2-ene. That's the IUPAC name. Amazing, isn't it? But you see, it's systematic. Once you've got the rules and you apply the rules, you'll see they're very easy to follow. Let's apply it to the next structure. Have a careful look at it. And the first thing that we notice is that there are the functional group. What's the functional group? Well, we've got 2 bromines there. This means that it belongs to the homologous series. Remember, a homologous series, something that has the same functional group and a similar general formula. And this is the one that we would call haloalkanes, because the other thing that we recognize is they're all single bonds. Carbon to carbon, single bonds. So there are 2 factors here to put it in this group. We've got a halogen, bromine. Now that could have been chlorine, or it could have been fluorine, or it could have been iodine. But we've got the bromine in. So we recognize it belongs to haloalkane. The other name, the alternative name for haloalkane, is called an alkyl halide. Right, let's get going. We always want to identify the longest chain, and we must identify the longest chain so that the functional group sits at the lowest number. So think for a minute, could I start numbering over here on the right hand side like I did before? No, because I want to make sure that I get the lowest number. So I'm going to start my functional group, my numbering at that position, because then the bromine will be on number 2. And now that one's on number 3, that one's on number 4, that's 4, that's 5. Now, if I go straight, I'm going to get to 6. But if I go down, notice I can get to 7. And that's the trick that the examiner wanted to get you to recognize. So what we realize is that we've got 7 carbons in the backbone, in the longest chain. We could redraw it in a straight line, and that would be perfect. Even here, it's perfectly acceptable to do it. So what is 7 carbons together? What's the prefix? Well, I hope you've gone through it. Remember them. We're going to say the prefix is hept. What else do we know? We identify between these carbons, they're all single bonds. So the suffix is ane. It belongs to the alkane. Haloalkane. Next, what else can we say? Are there any other special features? Well, yes, there's the bromo, and there's another side branch of carbon. So that's a methyl group. So we've got the backbone as being heptane. There's nothing else in that backbone. And then we've got interesting things happening at the side branches. Notice that we're using the alkane, or the halogen, as the most important side branch, because that determines our numbering. But when we do the order of naming, we've now got 2 bromos and we've got a methyl group. Which one should come first in the name? Should it be the one on the lowest number, or should it be some other form of naming? Now guys, here's the important thing. When we name, we always name according to the alphabetical order. So the bromo, B, comes before M. So make sure that you recognize that that must come first in the name, even though we're putting a prefix, because there were 2 of them, of di. So in this name, we're going to say, right, where is the bromo group? We know we've got 2, so there's 2 bromines that have been added, and bromine atoms that have been added. It's 2,3 dibromo. Now, where's the next thing? At carbon number 5, dash 5 methyl, and then what happens? It becomes the longest chain. So we're going to say heptane. Got it? Hope you can see that we break it down into those different segments. Now, the last one. the hydrocarbon that we see here, we've done quite a bit with this one. We recognize it's an alkyne. It has a triple bond, and we want that triple bond to be on the lowest number. So it doesn't take much to see that the lowest number will be starting from the left-hand side. We're going 4. We could go straight, or we can go up. So there are 5 of them. What's number 5? The prefix for 5, we're going to say it is pent. Yes, you've got it right. What's the suffix, the ending? Remember, prefix at the beginning, suffix at the end. The ending is -ine because it's an alkyne triple bond. Now, what are the other features that are in this molecule? There you go. You've got a methyl group. So we need to recognize the position of the triple bond. And so when we recognize that, we talk about position as well. So make sure you don't forget about position. Right, so let's start. Side branch first. On carbon number 4, we've got a methyl, 4-methyl. Then the next thing, it's pent. Make sure you join it. Where is the the triple bond? On carbon number 2. And that gives you 4-methyl pentyne. Now guys, I know that's been a mouthful, but I hope it's been useful in revising for you both the identification of functional groups and IUPAC nomenclature. We'll see you after the break. Welcome back from the break. Let's get into finishing off these questions now. So here's the next one. It tells us that compound D is prepared by reacting 2 organic compounds in the presence of an acid as a catalyst. Write down the homologous series to which compound D belongs. Well, guys, that's really easy. We know that when the formula ends in YL and then NO8, that belongs to the ester group. So there's no problem there. Notice what the formula was, pentyl propanoate. Pentyl means that there are 5. So we go 1, 2, 3, 4, 5. That's from the alcohol side. And then propanoate means that it's going to be, there's your ester functional group, 1 carbon, 2 carbons, 3 carbons. Now, just to save time, I'm going to just put in the hydrogens very quickly, but that will give you your structural formula of your ester. And we're almost done. Make sure you fill in all the bonds. Don't leave out a carbon, and don't just put in a dash. Let's go on to the next part of the question. It says, give the IUPAC name of the organic acid used to prepare the compound. Now, when you look at it, it's not difficult. The alcohol part was on the left-hand side, and the acid part is after with the carbonyl group. So there were 3, so that's propanoic acid. Excellent. Name or give the formula of the catalyst used. Well, very important, it's concentrated sulfuric acid. And if you had to give the formula, which might be easier to write, it's conc H2SO4. Now, let's move on. The next question is one that you won't find in other exam papers, because this is the first time you're going to get questions on polymers. So let's have a look at exactly what this question says. It says compound C, which is the polyethylene, is used to make plastic bags. Name the organic compounds used to produce compound C. Well, the monomer is very easy. It's ethene. Okay, we're asked to draw the structural formula to illustrate how it's formed. So ethene looks like this, 2 carbons with 2 hydrogens, and we have a whole lot of them. In the formula, we're going to put an N over there, and we recognize that addition polymerization takes place, and we then get this structure, which is the polyethene. What's happening is that double bond is broken, and it's by addition, and we get a whole lot of them. And it could be 500, it could be 5,000, it could be 50,000 to make these structures. Identify the type of chemical reaction, and we said it, I said it, addition, polymerization. And then the last two questions say, name one other compound that is made in the same way. Now, you should be aware that there are other polymers, not just polyethylene or polylactic acid. Those are the important ones that you need to study really hard. But there are others, like polystyrene, for example. And that's also made by addition polymerization, or PVC, polyvinyl chloride. Polyvinyl chloride. Make sure you revise what other polymers there are and the ones that you can take note of. Well, what other uses are there of polyethylene? Well, they can be made to make squeeze bottles, not just plastic bags, but squeeze bottles, or insulation for electrical things, and a whole lot of other uses of plastic. Not all plastic is polyethylene, but just be aware that it is an important type of plastic. Right, let's move on to question number 2. And here we're going to be looking at the structure, size, and take a look at the molecular properties and how the structure and size and shape influence the properties of the molecules. So we're doing an experiment, and it's a lab technician, unlabeled. She's got an alcohol, she's got an aldehyde, an alkene of comparable molecular mass. She takes a sample from each, and she's looking at boiling point. Now, let me just say something about boiling point. Boiling point is where the vapor pressure of the substance is equal to the atmospheric pressure. And so it can change depending on where you're at. But you need to be aware of that. For this investigation, we were given the samples and we were given the boiling point. So what's the independent variable? The independent variable is the samples that we chose. So we could say the sample, or we could say the type of functional group, because all the molecules were a different functional group. We're wanting to compare the effects that functional group has on boiling point. What's the dependent variable? Well, clearly the one that we don't control, boiling point. And as I say, make sure you understand what boiling point is. Now, from the passage above, we need to recognize why this is a fair test. Remember, in a fair test, other variables are excluded and controlled. So there are two factors: comparable mass and the fact that she does things under the same condition. If you identify those two factors, write them down, then you will get the marks required for that. Now, the next thing is the analysis of her results. And we're asked to analyze which sample is belonging to which functional group. P, Q, or R is the alkane or the alcohol. Now, here is the important thing. You need to recognize they have the similar mass. So it's not an effect of mass that is going to affect the boiling point. But the alkane has weaker intermolecular forces because it's a non-polar molecule. The alcohol has hydrogen bonds. So it's going to have stronger intermolecular forces. If it has stronger intermolecular forces, you're going to need more energy to break those bonds. So if we look at the substances we're given an aldehyde, an alcohol, and an alkane. The least polar of those is the alkane. So that tells me the one that requires the least energy is going to be the alkane. And so which one has the lowest boiling point? Remember, we have to put energy in, heat it up, so that it can melt, and then it can change from liquid into gas. And at that point, it starts to boil, it gets enough vapor pressure, we'll be able to say that's the boiling point. So the alkane, I'm going to say, is Q, and the one with the strongest intermolecular forces is R. And why do I say that? Because it has the strongest, it has the functional group gives you hydrogen bonds. Refer to the boiling point and the type of intermolecular forces between alcohol molecules to give a reason for your answer. And what we're going to say, we say this is the highest boiling point. And the reason is because it has hydrogen bonds. Now remember, those are intermolecular forces. They are not true bonds. They're not sharing electrons or anything like that. It's just the polarity because the molecule is most polar. Now, have a look at the next question. We're told that the alkane is identified as pentane. Okay, pentane because it's C5H. Now what? 10 plus 2 is 12. So it's got 5 carbons. Now, what we're going to, will the boiling point of hexane be higher than, lower than, or than that of pentane? So we're going to compare pentane and hexane. Hexane, C6H14. Got those formula, and make sure that you get them ready. But now read the question carefully. Which one's going to have the higher boiling point? Well, we've got to refer to the intermolecular structure. We've got to refer to the intermolecular forces and the energy. So let's do that. The first thing that we're going to recognize is that hexane is going to, I'm going to say that hexane will have the higher. Now we were asked to just say higher or lower. I'm going to say hexane is higher boiling point. Abbreviated. Why? Now, structure. First thing we're going to say with structure is that hexane is a longer chain. That means if it's a longer chain, it's got more surface area. And if it's got a bigger surface area, that means that it's the type of intermolecular forces. Notice we did structure first because they asked us to do the structure. What do we know about the intermolecular forces? Intermolecular forces. And if we're looking at intermolecular forces, we recognize they're both non-polar molecules. So they are van der Waals forces, and they are generally weak. You could even identify them as London forces or dispersive forces. But what we're going to say is that they are weaker. They're weak, but because there's more surface area, they're generally weak, but more surface area, there's more surface area means that they're stronger. There are more places for these intermolecular forces, more forces, more attachment in hexane. And what does that mean? It means that you're going to require, let's just extend the page, the energy that we're looking at. The final point that we were asked to deal with was energy. So if there are more forces, there are more bonds that are between those molecules, energy-wise, you're going to need more energy to break the bonds or to break the forces. I'm going to call them bonds, but they're actually forces in the hexane because there are more points of attachment. So get the idea in your head. Bigger area, more types of attachments, and so we've revised for ourselves the idea that intermolecular forces, structure and shape of molecule, influence the intermolecular forces, influences the energy required, which will influence the characteristic that we're looking at, which in this case was boiling point. Now guys, unfortunately, we've come to the end of today's session. Hope you've enjoyed it. Hope it's been an opportunity for you to revise organic chemistry and organic molecules. Remember, to practice and practice and practice. Join me again when we look at organic reactions. We'll see you soon.